Hello, in this video I have some more examples of molecular orbital diagrams. So, I call this a tour because we're going to start with the simple diatomics, start with element number 1, hydrogen, and work our way up. So remember, when you do these molecular orbital diagrams, and how to do this all is covered in the previous video on MO diagrams, you put before on each side. So here's one atom, here's the other atom. And then you put the after, you make a bond, you make the molecular orbitals. You put the after picture in the middle, and you connect them with these little tie lines. And your s orbitals can make sigma molecular orbitals, and you can make the bonding and the anti-bonding. And the anti-bonding has this little star on it. And then you go and fill electrons. Well, you have 2 electrons total, one from each hydrogen, and they'll both go into the bonding molecular orbital. Voila! Now, bond order, the formula for that is 1/2 times the number of electrons in bonding molecular orbitals, 2, minus the number of electrons in anti-bonding molecular orbitals, 0. You do that math, you get a bond order of 1, and then that matches our conception of hydrogen. It's a diatomic molecule, so you can make this nice little simple Lewis structure. They both have their duets, they're happy. That makes sense. All right, next up, atomic number 2, helium. So each 1s orbital now has 2 electrons in it. We have the same set of molecular orbitals. And now we have 4 electrons in here. So the bond order here is 1/2 times the 2 bonding electrons minus the 2 anti-bonding electrons. That equals 0. There's a reason why helium gas is not diatomic. Because if it were to make a molecule here, it wouldn't have any energy savings because you're putting as many electrons into the good as you are into the bad. It's equally good as bad. Okay, it doesn't make a bond. One of the cool things about molecular orbital theory, moving on, is that we can do these wonky ones that we couldn't do with Lewis structures. So we can have diatomic hydrogen that's a positive ion overall, which basically you have the sigma 1s and the sigma 1s star. And I'm just showing the molecules orbitals, the molecular orbitals in the middle. And you just take an electron out. All right, here's the hydrogen we just did. Here's helium as a diatomic molecule that's a positive ion. This would actually have a bond order of 1/2. Again, you can't call it a single bond. You call it a half bond. That's really kind of weird. Doesn't make sense with Lewis structures. But it does work, and it works here. You could also have H2 negative that would be the same as this. All right, and then here's the helium that we just talked about. So you can do all these kind of wonky things with molecular orbital theory. That's pretty cool. All right, moving on. Atomic number 3, lithium. Now, the question here, do you need both 1s and 2s orbitals? I always think it's better to start with the 2s because, well, your 2s is kind of bigger than your 1s. Your 2s is going to interact with the other nuclei. The 1s is not. You're not forming molecular orbitals out of this. But your book likes to use them, and so other books do too. I'm talking about Macquarie here, likes to use them. And so you'll see this sometimes with an identical looking set right below it that just says 1s and sigma 1s, sigma 1s star. Okay, right? I don't include that. I do want to make that clear that this is a difference between me and Macquarie. On an exam for me, either one is okay, but you have to be really careful when you're counting electrons. Going back to the lithium, well, lithium has 3 electrons total. 2 of them go in the 1s, which is buried inside, and only 1 of them is in the 2s. So we only have 1 electron here because we're only dealing with the valence electrons. All right, you got these 1 electrons. They come together and go in the bonding molecular orbital. The bond order here is 1. Okay, that makes sense. So you can have lithium diatomic. Usually lithium has other things to do and behave like a metal as opposed to make a molecule, but you can make this molecule in the gas phase, etc., etc. All right, there's this again. Now moving on, beryllium, atomic number 4. Again, I'm using just the valence electrons, so I only have 2 electrons for each beryllium. And then here's the electrons in the middle. And just like the helium case, Here, the bond order is 0, thus this doesn't form diatomic molecules. All right, moving on. Here's boron, diatomic. And now that you still have this complete set of the 2s and the sigma 2s, sigma 2s star. So this is still here. I just have it down below. You need to show it. Then the 2p is above it. Now, remember, you have this kind of diagram you might expect. It's actually wrong for boron, right? This is due to the sp mixing, which I covered in the previous video. But it's this idea that your sigma 2s and your sigma 2p occupy the same space and they repel each other, which is the memory trick. In reality, it's more complicated. It's this quantum mechanical phenomena of mixing. And the outcome here is that for everything except oxygen and fluorine, this molecular orbital goes above the pi. So you actually have this case. All right? And the trend overall looks like this. Your dividing line where your order of orbitals changes is between nitrogen and oxygen. So now we can go back to boron and make this the right way, where the sigma 2p is right here. And then fill electrons in. Okay, there's one electron in each of the p's. So they come in here into the pi 2p. The bond order is 1. And overall, this molecule is paramagnetic because there's unpaired electrons here. Whereas if the sigma was below, down here, then these two electrons would pair into the sigma 2p, and it would be diamagnetic. Now we can easily measure whether things are para or diamagnetic, so we know that this is right, because we can measure this is paramagnetic. Okay, in the previous video I showed the diagram for carbon, so here it is. The bond order is 2, because you're adding 1, 2, 3, 4, 5, 6 in the bonding, minus the 2 from the antibonding. So that makes 4. Then you divide it in half, and that makes 2. Another way you can do bond order is count pairs. 1, 2, 3, minus 1. But then you don't divide by 2, because you already did that if you're counting by pairs. Whatever works better for you, as long as you get the right answer reliably, you're fine. All right, we could keep going and basically just add electrons in and go through the whole list. And then by the time we hit oxygen, this sigma orbital is now below the pi, if we're going in order of increasing atomic number. I'm just going to show the diagram from Macquarie that does this for me, that has the kind of innards of the molecular orbital diagram, so it doesn't show the atomic orbitals on either side, but it shows you what the innards would look like. And again, as we talked about in the previous video, oxygen's paramagnetic because there's these 2 electrons here. So again, I discussed this in the previous video. Here's the things you have to do when you're doing molecular orbital theory. Make sure you know how to do these. Okay, so here's a kind of simple example. Draw the molecular orbital diagram for diatomic hydrogen, the negative ion, and then what's the bond order? And then you can already guess it's going to be paramagnetic because there's 3 electrons total. So somebody's going to be unpaired. All right, so the diagram looks like we've done before. Atoms on the side, molecule in the middle. This is small enough that we're only dealing with sigma from the 1s, and we're putting our 3 electrons in. So when you count for bond order, 1, 2 in the bonding, minus 1 in the antibonding, and then you take a half of that and makes your bond order a half. So this is a half bond. Sure, again, this is one of the advantages of MO theories, that we can do things like this where we couldn't do this before. Okay, so keep practicing. Again, it's going to seem very arbitrary when you first start playing with it. There's good reasons behind it. This is our best way of describing bonding that we have, that we talk about in Gen Chem. And just keep working at it till you get it. All right, thanks for watching.